I believe some books call what we're about to study Newton's law of cooling. And it concerns the rate at which the temperature changes in an object placed in a constant temperature surrounding. For example, if you pull out the Thanksgiving turkey from the oven and set it on the counter, and if the room temperature is a constant temperature, then the turkey is going to cool down. And at what rate will it cool down? Well, Isaac Newton discovered the relationship between these temperatures, and it's stated this way: the rate of change in the temperature of an object varies directly to the difference between its temperature and that of its surroundings. Now, we're assuming that the surrounding temperature is going to remain constant. And for example, the room temperature is 78 degrees and the turkey comes out at 190 degrees, then the turkey is going to cool down, but in this model we're not assuming that the turkey is going to warm up the room. The room is going to stay the 78 degrees. So, well, let's translate this to mathematics. So it's actually a fairly simple calculus-like relationship here. So how about we say that capital T of little t represents the temperature of the object at time t, time little t. So big T, little t. Big T is temperature, little t is time. And let's furthermore say that the, how about T R is a temperature of the surroundings, temperature of the surroundings. Now I put TR for temperature of room. So, but yeah, you can call it anything you want. Now, this will be a constant. This is assumed to be a constant. Of course, temperature of the object is what's changing. And so the rate of change in temperature, that's a derivative. So derivative of temperature with respect to time varies directly. That means there's a constant K multiplying the difference between its temperature and that of its surroundings. So rate of change varies directly to the difference between the temperature of the body and its surroundings. And again, when you talk about varies directly, you set it equal to by introducing this constant variation K. So there's our basic differential equation. And once we solve this equation, we basically have solved Newton's law of cooling. And we'll look at a problem or two. But let me do some erasing here to make room. So here's our differential equation. Again, I wrote it up here. And the two variables are capital T and little t. So I'm going to separate the variables by dividing by the parentheses and multiplying both sides by dt. So this gives me d capital T over t minus tr equals k dt. And the variables have been separated so we can integrate. And here, this is a logarithmic form. It would be the natural log, absolute value t minus tr is equal to kt plus a constant. And so we can verify that. Take this derivative, it's 1 over this function times the derivative of the function. Well, the derivative will be 1 minus 0, use the chain rule. Alright, well, let's raise each side to the power of e, and that eliminates those. So we have t minus tr equals 2. And over here I'm going to do the usual thing. Look at this as e to the kt times e to the c, and then rename this as a constant. So I have constant times e to the kt. And finally, if I add my other constant, temperature of the room, over to the right side, I've got my basic function describing temperature at time t. So this t, capital T, as a function of little t, will be c e to the kt plus tr. Alright, so we in the problems, normally the temperature of the surroundings will be given. And we'll need to know probably an initial starting temperature and another measurement based on how fast things are cooling in order to flush out this constant and that constant. So I'm going to make up a problem and we'll put all this into motion.